So for the test, what we will do is that you guys are allowed to navigate through the questions like you normally do, but the test will no longer be available for 24 hours. It will only be available for 3 hours on Thursday between 1 and 4 p.m. So during that 3-hour window, you will have 1 hour to answer 20 questions. You can freely navigate, and there will be a 3-hour window for which you guys can take the test. That will be the compromise.
Oh, so Miss, it's just 20 questions now with no short answers? Because I realize you
20
didn't say anything
questions.
yesterday.
The short answer probably like fill in the blank or match something. So it won't be like a essay type or sentence type short answer. Just gives
Okay.
a bit more flexibility in what we can test, if that makes sense.
Okay.
All
Thank you,
right.
Miss.
Any other concerns?
Dr. Stevenson, good afternoon. I think you should send what you just said in an email to the students for those who
Oh,
may not.
definitely, Marcel.
Yeah.
Yeah, definitely. The email will come out. We were just finalizing stuff just to make sure that we were all on the same page. So that will be sent out. We heard you guys loud and clear, and this is what we're going to do. But I please just ask you guys just to maintain the integrity of the test and of the exam, because the more we see that there might be breaches, the harder it is that we have to be on you. And I honestly, I don't think most of you, if any of you, would actually contemplate cheating on a test or doing something like this. But if one or two do it, it really makes it really hard for the others in the class. So that's where we're going from. All right, where is the test from? This is from lecture 5 all the way up to last week. And so that will cover some aspect of S block chemistry, the P block chemistry, and the introduction to transition metals and coordination complexes. All right, so everything there is fair game. I remember this exam is going to be fully open book and open internet and open everything. Okay, if there's no other questions, let's jump into today's lecture. Oh, the topics that we will be doing are from lecture 5 to last week's lecture. So lecture 5 would have been S block take 2, and then up until what we did last week. All right, so let's continue. So this is our third lecture, the second coordination chemistry lecture. The second lecture for our online edition, as we get used to this new platform. So last week we covered coordination complexes, and we were introduced to them. We then looked at calculating oxidation state, and we did the electron count. So for today's lecture, we're mainly going to focus on looking at isomers naming, right? And then if there are any questions or any other business, we'll discuss that after lectures there. As usual, Marcel is in the chat, so he can answer any questions that you guys may have as we continue. All right. So last week we left off with these complexes here, where we looked at this facial isomer, this chromium with this 3 chlorides in a facial arrangement, and we also looked at this other isomer, right, in a meridional isomer, right? So that's what off last week. So today we want to talk about isomerism, and you guys would have been introduced to isomers when you looked at organic chemistry. And the definition of an isomer is a molecule with the same molecular formula, right, as another molecule, but with a different chemical structure. And we'll talk about the different chemical structure. These chemical structure can come in 2 main forms. And the main forms, or the main flavors, are structural isomers and stereoisomers. So here are the big definitions. A lot of this lecture is basically going to be us exploring different type of isomers and looking at different definitions of them and seeing what structures fit those definitions, right? So bear with it. So for the first one, a structural isomer. Structural isomers are molecules or compounds having the same molecular formula, but with atoms connected in a different order. So if we wanted to summarize this, we say structural isomers have different bonds. The other type of isomers are stereoisomers, and these are molecules or compounds having the same molecular formula and sequence of bonded atoms, but they differ in their three-dimensional orientation of their atoms in space. So if we're looking at a stereoisomer, they'll have the same bond, but different spatial arrangement. All right, so those are the two main definitions that we're starting off with. Isomers, same formula, different atomic arrangements. And then structural, the atomic arrangements may be in what's bonded to what, or stereoisomer, we have the same type of bonds, but they're oriented differently in space. So with that in mind, the type of isomers that we'll be looking at are, in general, for coordination chemistry, are structural isomers and stereoisomers. And for stereoisomers, we look at geometrical isomers and optical isomers, or isomers with chiral centers. And for structural, we'll be looking at four types: ionization, hydrate, coordination, and linkage. Although hydrate and coordination isomers are pretty much the same, just that in one case you're dealing with water and the other one you're dealing with anionic ligands. Let's jump into it. So let's do our first poll and let's see if we are actually paying attention. So if we look back at a definition of different types of isomer, what type of isomer are Fachner isomers? Are they structural, stereos, or are they even isomers at all? Right? So what do you think if we go back to the definition? All right. So let's give you guys 30 seconds to work on that. All right, so, okay, let's look at our responses. So far, our responses are showing 45 people abstaining. I hope you don't do that on Thursday. We have 10 people saying structural and 65 people saying that the answer is stereoisomers. So if we go back to our drawings and look at it, remember that structural isomers are going to have different type of bonds, whereas stereoisomers have the same bonds but different spatial arrangement. So if we look now at our isomers, we'll see that they all have the same type of bonds, right? For the most part, so they have the same bonds. So nitrogen bonding to chromium, nitrogen bonding to chromium, chloride to chromium, chloride to chromium, chloride to chromium, right? And then it's pyridine to chromium. So they have the same type of bonds, but what's different here is the way in which they're structurally, their spatial arrangement, the way in which they're arranged in space. So the answer for this, the B's have it. So these are examples of stereoisomers. Same bonds, but different spatial arrangements. Good job. And hopefully for those of you who weren't sure or chose A, you can now see more clearly how to difference between a structural and a stereoisomer. So not only are there stereoisomers, but Fachner isomers are a type of stereoisomers called geometrical isomers. right? And geometrical isomers arise when atoms or groups of atoms assume different positions around a ring, bond, or group. So FAC and MER isomers are geometric isomers, right? So if we look around the chromium center in the example shown here, we can see that there's different arrangement of my ligands around the center metal atom. Another type of geometrical isomers are cis-trans isomers. So again, here is an example of cisplatinum and transplatinum. And if I investigate my metal center, I will see that I have two ammonia ligands 90 degrees apart in this square planar geometry, and the same thing here. And in this case, the trans one, they're 180 degrees apart. Typical to what you'd see in organic chemistry when you're looking at alkene chemistry, right? And so cis and trans, again, are also geometrical isomers. So if we look at geometrical isomers, a 3D representation of cis and trans platinum. And what you need to make sure that you are aware of is that when something is cis, there are 90 degrees apart. And then when they're trans, they're 180 degrees apart, right? So here in cis, my chlorides are 90 degrees. In trans, they're 180 degrees apart. And this is important for the type of chemistry that these molecules will do. So cisplatin is actually a chemotherapy agent. And once it gets, you can give it, once you dose it to a patient who has certain types of cancer, such as prostate cancer, it gets into the cell, it will undergo hydrolysis. And the cool thing is that the cis version of cisplatin will actually find DNA that needs a repair, bind to it, kink it in cancer cells, because cancer is going to take up medicine faster than normal cells. And then once it gets into the cancer cells and it's basically links to your DNA, it's going to kink it, make it basically damage the DNA, and then your cell apparatus can see that this cell is damaged, and they can then bring it on, send it along for apoptosis or cell death, killing the cancer cell. So cisplatin is a chemotherapy medication. Transplatin, so if we had these group trans instead, so for ammonia were trans instead, this is not an effective therapeutic agent, and in fact, it will just kill the patient if it was given to us. So geometry is really important when we talk about how these molecules behave, and the chemistry is always linked back to the structural arrangement of these atoms in these complexes. All right. So we can also have cis-trans isomers in octahedral complexes. And so here we're now giving you two complexes to the purple. We use the purple for the purple color, and they're based. So if we look at this, it's a cis with cobalt, 2 chlorides, 4 ammonia, and these are cations or complex ions. So if we wanted to draw the cis, right, it means that my ligands have to be 90 degrees apart. So now if we look at an octahedral structure, we should realize that if we're looking at something that's 90 degrees apart, so if I were to put, okay, I have 2 chlorides here. So if I'm going to put those 2 chlorides 90 degrees apart, 1 chloride can go here, and 90 degrees from this here is either a center here, this is 90 degrees, or this one here is 90 degrees. So if I want to draw the cis version, I would add my other chloride here, right? Or I could add it on the other side. And then I can then put in my ammonia molecules. And it's an ion, so we'll put the +1 there. So that will be the cis. Can you guys now guess if we had to draw the trans isomer of this compound? And if I place my chloride in the same position before, where would the next chloride be in order for it to be trans? At the bottom, exactly. Oh, someone's drawing. All right, cool. I thought I disabled that. Great, awesome. So if it's trans, again, it's going to be 180 degrees apart. And where that's going to be is at the bottom. Thank you. All right. And then we can fill in our NH3. And again, I'm showing you the pictures of these complexes, and you can like actual colors of them. And what you can see is that just that one change of a ligand, whether being trans or cis, can now change the way in which the color of the complex is, right? So in this case, the cis molecule, it's purple. In the case of the trans molecule, it's green. And this is telling us that there's something happening on the electronic level based off just having these different types of arrangement around our cobalt. And I think that's pretty cool. All right. So another place we can have cis-trans isomers are with bidentate complex. So we've looked at some ethylene diamine complex before. So here is two. All right, again, we're looking at cobalt. It has two chlorides and two ethylene diamine ligands around it. So these are going to be bidentate ligands. So if we look at the first example and we look at our chlorides, right, we can see that they're 90 degrees apart. So therefore, my chlorides are going to be cis together, are going to be cis, right? And then the geometric isomer of that would be now if they're 180 degrees apart, right? One up top, just as we saw before, and then this is now the trans isomer, right? So again, for octahedral complexes, these are examples of geometric isomers of cis and trans isomers in bidentate complexes. And we're going to see these again, but for now, we'll just move on. All right. Okay, so let's move on. All right, so those geometric isomers, the other flavor of stereoisomers, like how we're looking at stereoisomers, are isomers with chiral centals, right? And these in general are called optical isomers. And optical isomers are kind of cool. And it took chemists a while to note that certain compounds or certain molecules can have optical isomers. Not just that they can have optical isomers, but that it's actually very important the way in which these optical isomers interact with the world. One famous example is with the children of thalidomide, where a drug was made that had a chiral central, but um, both versions of the drug was sold, and it caused birth defects in children, right? And so since then, if you have a molecule with a chiral center, I'm assuming you guys know what that word means from organic chemistry, that you have to be careful to know how it's going to affect with the body. So just like in organic chemistry, you can have optical isomers, you can have chiral compounds and optical isomers for transition metal complexes, right? So again, optical isomers are going to be two compounds with the same atoms and connectivity that are non-superimposable mirror image of each other. In other words, they're chiral compounds, right? And chiral is a fancy way of saying that we have asymmetry in the molecule, right? So if we look at over here, right? Here I have cobalt with a bromide, an iodide, a fluorine, and a chloride ion around it. And if I were to take an imaginary mirror and then I were to now draw the mirror image of this, so because bromine is here, it's going to be over here, chloride remains the same, fluoride is here, and iodide is the same. And now if I try to bring these two molecules together to put them on top of each other, it won't happen, right? So they're non-superimposable. I can't take one and put on top of the other. And these are called non-superimposable mirror images, right? Furthermore, if I wanted to know if I do have, if I look at a molecule and I want to know, is it possible to have chiral centers? What I really can you guys hear me now? Okay, awesome. All right, where do we leave off? Sorry about that. I think my hand touched the mic at the bottom. All right, where do we leave off?
Miss, just talk about what you were saying before you start making the excess glue lines.
Okay. All right, thank you. All right. So what I was trying to say is how we can tell if a molecule is in fact chiral or will have chiral centers. So in organic chemistry, the first thing you guys learn is that if you have a carbon with four different things around it, it is chiral, right? And that is true. And the reason why this is true is because that molecule does not have a line of symmetry, right? It's asymmetric. So if I were to get rid of my lines that I started with, right? And this tetrahedral cobalt with 4 different ligands around it. If I were now to place, to try to see if there's a line of symmetry, so if I were to draw a line this way and look at what ligands were on the left-hand side and the right-hand side, I see that it's different, so it's asymmetric. If I were to draw a line in this plane, right? Let's call that the y plane, and look again, I can see that they're different over here. And if I were to draw a plane in the other direction, line here, I'll see that even in this direction, that there's no symmetry in the molecule. So wherever I have a molecule that doesn't have any symmetry in there, it's going to give rise to chiral molecules, or its mirror image is going to be non-superimposable. All right, so let's look at some examples. All right, just to summarize. So again, so optical isomers, they're going to have non-superimposable mirror images. They're going to be chiral. And besides how they orient in space, they're going to have the same physical property. So they're going to have the same boiling point, the same melting point. They're going to have the same, if you do an NMR spectra, they're going to have the same NMR spectra, the same mass, everything is going to be same. The only thing that's going to be different is how they interact with plane polarized light. And the reason for this is because plane polarized light is actually itself chiral. And I'll show you an example of this on the other slide. All right. Whenever I have optical isomers, they are called enantiomers. That's just a term we use, right? And the big takeaway is that these are asymmetric molecules that have no plane of symmetry. And it's possible for tetrahedral and octahedral complexes. However, for tetrahedral complexes, they tend to have ligands labile ligands moving around. So therefore, we'll mainly see them in octahedral complexes. And we'll talk about that part of it in our last lecture when we look at stability constants. Okay. So here is plane polarized light. So if we take a light, right, it's going to have wavelengths going in all different direction. But I can put a filter in, and this filter can then select for one type of, so plane polarized lights, right? So one type of light. In the presence of a chiral compound, and here I'm showing you some organic molecules, depending on how these molecules are going to interact differently. So in the top example, it's going to rotate the light to the right, and the bottom example is going to rotate it to the left. And that's how we can tell whether or not we have chiral molecules. It is how they interact with plane polarized light. And this happens because plane polarized light itself is chiral. All right, don't worry, you won't be tested on that. I just think it's cool and wanted to share that with you. All right. You tell me, Pinnock, which one is R, which is S? All right, so here is another molecule. So here is iron with 3 chlorides and 3 fluorides. Okay, so first away, so the first thing we should be looking at this is to now think about one. We should notice one type of isomerism right away looking at this molecule, right? We've already discussed this, right? So we can say that there's a geometrical isomer possible here, correct? right? Right? And we should be able to tell that this is going to be a facial isomer. So the question is, does this molecule have optical isomers? What do we think? Does it have optical isomers? So what's the test? The test is to look to say, well, if it's an octahedral complex, the first thing we want to say is, does it have 6 different things around it? Then we know right away that it has optical isomers. But the next we want to look at, is there a plane of symmetry? Is there a way I can cut this molecule either in the Z plane, the X plane, or the Y plane and end up with a symmetrical molecule? All right, so let's look at it. So if I were to, let's use black with this one. If I were to now try and cut this molecule down the Z-axis down here, how does that look to you? If we go straight down, we realize that yes, there's a plane of symmetry right down that molecule. Right, Damien? See it, right? So therefore, the fact that we can stop right there, right? There's more of them. But the fact that we can see that plane of symmetry is going to be like, okay, that's symmetrical molecule, therefore it's achiral, optical isomers are not possible. The only isomer this thing is capable of, from what we can tell right now, is a geometric isomer where the chlorides could be on the meridional, could be meridional instead of in the facial arrangement, right? So yes, definitely we have isomers. All right, great. And this is not, we have geometrical isomers, but no optical isomers. Hi, Nadesha, what's up? You can speak.
Miss, can you go over that again for me, please?
Where do we lose you?
Cut
All right.
molecule
So,
together.
all right.
Yeah, that
So
part.
when we look at any molecule, right, whether it be organic, inorganic, a molecule in general, and we want to know if the molecule is going to have, can have optical isomers, right? Does it have a chiral center? Can the molecule be chiral? What we're looking for is, what we look for are planes of symmetry, right? So in this case, now I'll just get rid of the one, sorry, before, is that we can either, there's 2 ways of doing it. We can draw the mirror image and then try to put the mirror image on top of each other to say they're superimposable. But another way of doing it is just looking for asymmetry within the molecule. And so in this molecule, I said before, we can look to see, is there a point of symmetry? So if we were to cut, remember symmetry means going to have the same thing on both sides, right? So if we were to cut this molecule just down this way, right, we'll see that on the Z plane, we'll see that there's a plane of symmetry here, right? If I was even to rotate this molecule around, we can see it can rotate back on itself, but all the time. But right here, down here, if I look at this side, blue ball, green ball, and blue at the top, green at the top, it's symmetric, right? I can even cut it through here, right? Not really so much because top and bottom is different. But once I find a plane of symmetry, it's telling me that the molecule cannot be chiral. It's not asymmetric. And asymmetry is needed for us to have optical isomers. All right, so this is achiral. All right, let's move on. Okay, how about this one here? So here's another example. And in this one, we have cobalt with 2 ammonia ligands, 2 iodines, and 2 chlorides, and they're all cis to each other, right? So if you were to draw the mirror image of this, just in case you were asked, how you draw the mirror image of this. So anything close, so NH3 would be here. The easiest ones to draw are my chloride, so my active ligand, so chloride and iodide. Wait, hold on. Yep. And then we have chloride here, and then iodide here. So my question to you is, does this molecule possess a plane of symmetry. I see yes and I see no. I see a lot of no's. All right, I think I'm seeing more no's than yeses.
Repeat the question, please.
Does this molecule have a plane of symmetry? Is this molecule chiral? And so in interest of time, the no's have it. So if we try and good job, sometimes it takes a while to actually see, to be able to see things in a three-dimensional space, to see three-dimensional objects on two-dimensional space. So for those of you who aren't seeing it, you're at home. If you have styrofoam balls and sticks, make an octahedral complex and try it. If you guys have flour and water and matchsticks, use that to make an octahedral and some food coloring, make a model, and then make the mirror image of it and see if you can actually superimpose them on each other so you can actually see and look for those lines of symmetry. All right, so let's look at it again. So last time we looked at this molecule, we went straight down the middle. We said, do we have a line of symmetry? And here, if we went down the z-axis again, we realize that there's two different things on the left-hand side and on the right-hand side, right? If we cut it here along, let's call it the y-axis, we have, again, no symmetry on either side. And if we were to cut it along here, we see that, again, there is no symmetry between the top half here and the bottom half here. So because of that, we can tell that this molecule is indeed chiral, right? And it has a non-superimposable mirror image, right? So it has no plane of symmetry. Hi, Michaela, what's up?
Miss, I just want to clarify something because there are different groups on the, the arms or whatever. It's not symmetrical. That's what you're saying.
So, all right. So when we talk about symmetry, what does symmetry mean?
You can divide it and get the same, or they can
Right.
hold on each other. Yeah.
Right. So basically, right. So you can divide and get the same, right? So in the example before, you saw that when we divided in the middle, it was the same thing on both sides. Was that clear?
Yes, Miss.
All right. So for this one, it's the same exercise. If we were to divide that molecule down the middle or in any plane, right? Do we get the same thing? Is it symmetrical? And from this
No,
example, mm-hmm.
Miss,
Continue.
continue.
No, you continue. Go on.
No, Miss, I agree with what you're saying.
Oh, I said I want you to continue, so it will save me some some talking. Right. So if we start looking at cutting it down in different planes and looking for different symmetry elements, we see that it's asymmetric, right? That
Yes, Miss.
the way in which things are oriented, there's no symmetry in the molecule. And so if that's the case, then it means that it means that this molecule will have optical isomers. Its mirror image is going to be non-superimposable, so therefore it has a chiral center. All right.
Okay. Thank you.
So Dustin, to answer your question, because I'm seeing it now, no problem. Is that can we count the number of groups around the carbon? If there is at least 4 different groups, then is it chiral? And so that doesn't work for an octahedral complex. So it will work for an octahedral complex if you have 6 different groups around the molecule, right, around the central atoms. If you have 6 different ones, you can look at that and say there's no way we're going to have any symmetry because there's 6 different groups around the central atoms, which is similar to carbon. Carbon can only form 4 bonds, 4 different things around it. There's not going to be any symmetry. But for the octahedral complex, what we have to keep in mind is how the ligands are oriented in space. All right, and as I look through, we'll see other examples. Let me get to that. All right, so we're going back to our bidentate ligands, right, with cis orientation. And so if we look at, if we examine these molecules carefully, and here is, in this one, it's trans chloral, right? I can look right away and say that, yes, there is a line of symmetry in this molecule. If I were to cut it here, or if I were to go through this plane, this is symmetrical, so this can't have optical isomers. However, if I were to look at the cis isomer, what you will notice now, so here I have cis, so these are geometrical isomers, trans and cis. In the cis isomer, this ethylene diamine group here is basically being twisted. It's twisting in that direction there. And this ethylene diamine group here is called towards you, right? Towards the board in this direction here. And so when that happens, there actually causes this to have a plane of asymmetry in this molecule. So in general, if you have an octahedral complex with bidentate ligands with cis orientation, chiral centers, you have a chiral center, and so therefore you can make a pair of enantiomers from this, right? So general rule. And if you were to take the mirror image and try and superimpose them, there'll be non-superimposable mirror images, right? And this again comes because this paddle wheel structure here, where now this arm of the ethylene diamine ligand is sticking again back out that way, this one's coming up forward. And so when you try to put them together, they're actually in different orientation. And so therefore, these will be optical isomers. Right. Another place for optical isomers in octahedral complexes is if we have 3 bidentate ligands attached to the complex. So when we made, in lab, we made potassium trisoxalato chromium species, right? So we had chromium with 3 oxalate ligands there. And for those who are in my section, we discussed that this was actually a chiral compound because it was asymmetric, right? So if we were to have now, here's cobalt with 3 ethylene diamine ligands in there, right? 1, 2, 3. This is going to be, these are going to be chiral molecules, right? Again, the easier to see this is to draw the molecules themselves, or to construct the molecules themselves, make the mirror image, and try to superimpose them. And you realize that there is no center of symmetry. We can also use this representation here, and we can kind of see it. So if we were, like, again, cut down in the center here, we'll see that if we look at the left-hand side and the right-hand side, that they're different. If we were to go in this direction, we'll realize that the molecule is different in that direction. If we were to go in that direction, the same thing. And so this molecule is chiral, as there is no plane of symmetry because of how the carbon chain on the ligand is oriented, right? So when we see molecules like this, they form a helix. If I were to look straight down the center of my cobalt, I present it like this, right? And depending on the orientation of my ligand. So in this case, so for instance, in the example on the left, you will notice that my ethylene diamine ligand right here, right? One here and one here, kind of like a fan blade. And in this instance, you'll see that my topmost ligand is now going to the left-hand side, right? So it's to the left, right? And we'll call this the lambda, right? So the ligand's left-hand side of the helix, we'll call this the lambda isomer. If we look at the other one, we will notice now that my ligands are now, my paddle wheel goes to the right, right? Where now my top one, most one, is now on the right-hand side. And this will be the delta isomer. Right? And so those two are also optical isomers. All right, that was fun. So we've gone through stereoisomers, and that's all we'll be looking for stereoisomers. And now we're going to take the last 15 minutes of class, and we're going to examine structural isomers. Are there any questions on this? And don't worry, we'll have a nice tutorial on this, and you guys will get all the practice you can get. I'm sorry that your brain is fried, but we really do have to get through a lot of this material. Yes, Nadesha. Pick one
Miss,
question.
does the left hand and right hand helix only apply to bidentate ligands?
It applies to these paddle wheel structures. So once you have once you have these bidentate ligands on them, and the way in which they orient, it's going to form left and right, especially when you have these tris bidentate complexes.
Okay.
Right. So if you look down the plane of it, it will look like a fan blade. Right.
Okay,
And so
miss.
therefore, these two images, these two structures, the mirror images of it is not, they're not superimposable, so they'll be chiral. All right. So lambda is left, delta is right. Okay. All right. And there are other notes on ORVLE that will go into I have a bit more detailed notes there, so you guys can look at that. Also, you'll notice a lot of these graphics are coming from Chemistry 3, and the chapter or the pages on this is on ORVLE. You guys can read through it if something, and that will give you some other context and some other examples. All right, so let's move on. All right, so we said before that there were two main branches of isomers. We could either be stereo or structural isomers, and we just looked at stereoisomers, which are sometimes difficult to see because they require us to be able to look at, again, two-dimensional objects and two-dimensional space, and to be able to look at molecules and orient them in space to see exactly, are they symmetric? Do they have planes of symmetry? Are they chiral? Are they asymmetric? And that can take some time to get used to and some practice. But structural isomers tend to be a bit more easier to see because, again, we have different types of bonds. So just they look different, right? So we're going to discuss ionization isomers, coordination isomers, and linkage isomers. We won't discuss hydrate isomers. I can briefly tell you what they are as we move along. And you see them in tutorials along with relevant explanations. All right, so an ionization isomer, and these are compounds with the same chemical composition, again, they're isomers, but differ in position of an anionic ligand, right? And right, and so the anionic ligand may be bonded either within the first coordination sphere, that means either bonded directly to the metal, or it could be the second coordination sphere, which means a counter ion. So these are going to be isomers where have the same molecular formula, but one of my anionic ligand, whether it be sulfate or chloride, it may either be attached directly to the metal center, or it could be serving as the counter ion. And these are ionization isomers, right? So I'm showing you here two compounds in purple and red, their actual colors. And in the first one, you can see in both cases, we have cobalt with 5 ammonia ligands around it. In the first one, we have a bromine that's in our parentheses, which means that bromide is attached directly to cobalt. In the second one, we still have 5 ammonia ligands, and now we have, or now is now serving as a counter ion, right? And now sulfate is now attached to the cobalt in this red example, where sulfate is now the counter ion in the second example, right? So these are ionization isomers. So how can I tell if I have ionization isomers? And your tutorial this week, question 4, is actually a question, is about ionization isomers, right? So how we can tell is basically to see how the counter ion behaves in solution. So if we draw the structure out of these two compounds, again, here is bromide bonded directly to the cobalt in the first coordination sphere, right? And the second one, sulfate is bonded. But again, same molecular formula, just different bonds to the metal center. All right, so how do we know which one is which? So here we have our compound again. If we put these in water, remember that when we put a coordination complex in water, that whatever is in the square bracket is going to stay in the square bracket, it's going to be bonded to my cobalt. And now I'm going to have my counter ion, my sulfate ion is going to be, aqueous sulfate is going to be in there. Can anybody tell me if I wanted to test to see if my sulfate was in solution, right, attached to my cobalt, what test could I use to test for sulfate?
Barium chloride.
Barium chloride, brilliant. Right. So if I threw some barium chloride in there and I get a white precipitate out, I know I've made barium sulfate, which is not very soluble, and which you remember from eons ago during those lectures why barium sulfate is not soluble in water, right? And so therefore I get a white precipitate out. And that's a positive test for sulfate, which means that sulfate was my counter ion. All right, now. So what do you think will happen? What's the test for bromide?
Silver nitrate.
Silver nitrate. Look at some of the row. So if I add silver nitrate now, I get no precipitate. So I can do a mass and it can tell me that I have, or elemental analysis, it can tell me I have bromide in this molecule, but because I add silver nitrate, I get no precipitate. That tells me that that bromine ion or the bromide ion is attached directly to my cobalt center, right? Okay. So now what happens now if I were to look at it the other way? All right, so for the second example, what do I expect to see if I add barium chloride solution?
White precipitate, but no precipitate.
All right, so Davion is telling me that he's expecting to see no precipitate if I add barium chloride to this. Anybody else?
Second.
To the second one, yeah, we want the second one though, the other one gray out. Damien Clark is agreeing, Alonzo agrees, Tia, and Jean, no comment? All right, yes. So if I were to add barium chloride to this, Regin's like, I don't know, but I'm cheering on Devion in the comments. All right. Again, when I add this into water, right? When I add this to water, whatever is in the square bracket is going to be bonded to my cobalt, and it's not going to, right? It's going to stay bonded solution, and my counter ion is going to be free. So barium chloride will give me a positive test for sulfate, but only counter ion that is free in solution can react with my barium chloride. So in this example, the sulfate is tied up to cobalt, so therefore it can't react, whereas bromide, right, is only counter ion in solution. So therefore, if I were to add siltrate to this instead, I would expect to see a precipitate with silver nitrate, but no precipitate with barium chloride, right? And that's what it looks like, right? So silver nitrate now give me yellow PPT, and barium chloride would not give me a precipitate. All right. So another type of isomers are coordination isomers, and this one usually is a bit tricky for you to get. So let's see if we can walk through this slowly. So coordination isomerism, and those of you who Google is your main source of information, be careful with this one because a lot of sites confuse coordination isomers with ionization isomers, right? But the definition for coordination isomer are compounds where the cation and anion are complex and they vary by the distribution of the ligands, right? So let's look at this. So here is one compound, right? So in this, I have cobalt with 6 ammonia ligands around it. It's a cobalt 3+. So therefore, the overall charge of this complex here is going to be 3+. So normally I could do something like I could either find 3 chlorides and I can balance that charge. But I also balance the charge and make a compound with another complex anion, right? So over here, now I have chromium 3 with 6 cyanide ligands around it. So therefore, the charge in its overall complex is going to be 3-. And so these two can come together to form one compound, right? And if you want to think of it, you can think of it as a very big sodium plus and a very big Cl minus, right? They come together to form ionic compound, right? So so when we have these types of complex compounds from where the cation and the anion are both complex, the type of isomers we have is called a coordination isomer, right? And how that looks is that in the first case over here, we have cobalt with 6 ammonia and chromium with 6 cyanide. Another way of representing this is that we could have another complex in which chromium is surrounded by 6 ammonia and cobalt is surrounded by 6 cyanide ligands, right? So this is one compound and this is its isomer. And these are examples of coordination isomers, right? And that's all we're going to do for that for now. So the last one we look at are linkage isomers, and I think these are kind of cool. And linkage isomers are coordination compounds, again, with the same chemical composition, but they differ in which donor atom of an ambidentate ligand is connected to the metal center. So if you see the word ambi, you should be thinking of ambidextrous, amphibian, which meaning both, right? So some examples of ambidentate ligands are showing you over here to the left-hand side, right? We have the nitrite ion, we have DMSO, dimethyl sulfoxide, and we have the thiocyanate ion. So we know that for a molecule to be a ligand, it needs to have a Lewis base, which means it needs to have an atom that has lone pairs around it that it can donate towards bonding. So if we look at the nitrite, ion, we'll see that both the oxygens and the nitrogen both possess electrons. And so either one of those can bite into a metal center. Sorry, this oxygen is a metal one to choose. Sorry. Right. So either one of those can actually coordinate to the metal center. Same thing for thiocyanate ion. So again, here's nitrogen and here's sulfur, right? Both lose basic side. So either the nitrogen or the sulfur could coordinate to a metal ion. And for DMSO, again, here is oxygen and here's sulfur, both having lone pairs, and either one of those atoms can coordinate to the metal center. So an ambidentate ligand is simply a monodentate ligand containing more than one possible donor atom. So depending on the metal, the oxidation state of the metal, it's going to determine which one, whether for nitrite, whether you bind through the oxygen or through the nitrogen, or for DMSO, whether you bind through the sulfur or the oxygen. That kind of stuff is outside the realm of our class, so don't worry about it. What I want you guys to take away from this is that for molecules or for monodentate ligands that have more than one donor atoms, linkage isomerism is possible. All right. So again, if I have nitro NO2, I can form a nitro compound if my nitro bonds to my metal. So M is just a generic metal. If it binds to the oxygen, I have the nitrito complex, right? And it goes through for oxygen. For thiocyanate ion, if it binds through sulfur, it's a thiocyanate complex, or if it binds through nitrogen, it's the isothiocyanate complex, right? Again, monodentate ligands containing more than one possible donor atom. So here's an example. And so if we look at these two examples, we have cobalt, and if you notice here, the way in which it's represented in the formula, right? In this case, O and O, that means that we have a nitrito. So if I were to draw this complex, it would be cobalt through oxygen, nitrogen, and oxygen, right? That's the nitrito. It's being bonded. Nitrite is bonding to cobalt through the oxygen atom. And on the other side, we have nitro, right? Where now it's bonding through the nitrogen atom, right? And because of which atom is binding to the metal center, if we look now at the properties of the salt they make or compounds they make, we'll see that they have different colors, which means that whether you're binding through oxygen or nitrogen is going to affect the electronics around the metal center, right? Giving rise to different color. So if I were to have these two complexes and I know a mass, I know that I have a nitro group in there. And if I really want to know if it was bonded in the fashion of a nitrito or a nitrite, I could use IR and look at the difference in the searching frequency in the IR to differentiate one from the other. All right. So by the end of this 2 classes, you guys should be able now to work oxidation state of the metal ion coordination compound from its formula. You guys should now be comfortable working with oxidation state of metal in a coordination compound, its valence electron configuration, and its coordination number. And there's lots of practice on both of these on this week's tutorial, right? And now the skill that we should start on for this session is to look at now a coordination complex and tell if isomers are possible, right? And describe the type of isomerism that's possible. And, you know, just to add, we can see if we've absorbed anything at all during this last hour. And I give one question to you, right? And it is, identify each of the following pairs of coordination compounds or complex ions as coordination isomers, ionization isomers, linkage isomers, optical isomers, I misspelled isomers here about that, or geometric isomers, all right? So for the first example, what kind of isomerism are we seeing?
Ionization.
Ionization, all right, great, and it's ionization is popping up in the chat room, love it, okay. And for the second one, what do we have?
Stereo.
What type of stereo? Go on through, Miss Pinnock. So the geometrical isomers, all right? And then for the last one, what do we have for 3? Yes, Justin, we have coordination isomers, all right? It's 6 o'clock. Thank you guys for your time. We didn't go through naming here, and traditionally I usually put naming on a tutorial and give you guys the rules. I send you off for you guys to practice. But for some strange reason, I thought that we'd be able to get through naming of coordination components in class. It's not going to happen. So look for your next tutorial. I'll give you the list for how to name coordination compounds, and we will have practice in the tutorial sessions where we can have more one-on-one time. No, this will not be on the in-course test. In-course test material stopped last week, so don't worry about it, right? And so the slides are here, and the rules are here for naming complexes, and you guys can practice. So next week, we're going to be talking about crystal field theory. Please review d orbitals, right? How many d orbitals are there? What's your orientation? Why is the dz squared orbital called that? Why is dx squared minus y squared called that? How is it oriented in space? That will make next week's class a lot easier. And then after that, our final class is going to be on stability complexes. One last thing is that next week, we may move to Zoom. I really want to do some demonstration for next week's class. And so please look out for an email if you're going to move platforms from Blackboard Collaborate to Zoom. If I can figure it on Blackboard, we'll just do it on Blackboard. Have a wonderful rest of your evening, and I'll see you guys whenever. All right, bye.